Before we get into today's topic on the anti-lag stuff, a quick update on our Rex engine. So track day 1 went very nice. And yeah, moved over to track day 2 from there. Yeah, as you guys can see, I mean, track day 2 already sounds much better, so it sounds like a race car and not just some popping and banging like a hobby or a drift car or something like that. So big progress on the Rex engine. But yeah, let's get into today's topic. So anti-lag for dummies. Let's start with some quick basics. So we're going to be going through performance and reliability focused anti-lag. So if you're here to look at pops or bangs or flames out the exhaust like system or something like that, then you're on the wrong video. But yeah, let's go forward with the stuff. So with anti-lag stuff, in this video we're going to be going through that related to turbochargers. There potentially might be other use for it also, but this is what we're looking at in this video. And of course, a turbocharger consists basically of a turbine wheel and a compressor wheel with housings around those, and they have efficiencies and stuff like that, but we're not going to get too deep into that in this video. So the compressor works, it takes ambient air or air from the intake to the turbocharger compressor and moves that up to a higher pressure area, and that of course takes energy. And because this is a continuous process, energy over time of course is power. So you need a power input to the compressor wheel for the turbocharger to function, and that power comes from the turbine wheel. So you have to have a pressure difference over the turbine wheel and some kind of a mass flow through that to get power output from the turbine wheel to power the compressor wheel. And the higher of course the mass flow and the higher the pressure ratio, generally the more power you're going to be producing in the turbine wheel. And if you're producing more power in the turbine wheel than the compressor wheel minus the losses, then yeah, you're going to be spooling up the turbo and increasing the turbocharger RPM. And this sort of RPM on the turbocharger is basically what lag comes from. So it's lag and power bandwidth are completely separate topics. So we don't want to get these confused. So you have some kind of a power band. So you have the so wait, you're looking at this direction. So you have the minimum engine RPM where you can get your desired boost. That's basically your minimum RPM. This might also be dependent on the choke limit on the turbocharger. And then at the top end you have typically the maximum RPM of the engine, or you might have a choke on the turbocharger compressor also, or extremely high back pressure on the turbine section, so you're limited on that section. Then on the lower end, of course, you're not really limited there at all. You can run as little power as you want. And on the top end, you're limited by boost pressure or potentially knock threshold. If you have a very knock limited engine, then yeah, you might not want to run maximum amount of boost pressure and instead lower the boost pressure to be able to run a little bit more ignition timing to get the maximum power out of the engine. So this is basically your operating window. And inside this operating window, when your sort of engine RPM is in here somewhere and you step on the throttle at low RPM, for instance, and you have some lag until you reach your desired boost pressure, that's lag. So if you're outside of the operating window and revving up the engine, then that is not lag. Then you're not in the operating RPM of the engine. So these are separate concepts and important to know. And while the turbocharger operates on a sort of mostly continuous basis, so you have a continuous RPM and it's feeding continuous air in and exhaust gas out through the turbocharger, which is producing the power and consuming the power in the turbocharger. The engine, on the other hand, works on a sort of quantized function, so it's not operating continuously at all, but each cylinder is operating basically independent of each other. Of course, the average intake and exhaust pressures are going to be the same because they're ducted together, of course, but each cylinder operates different from each other, so you can have varying air-fuel ratios between each cylinder, varying ignition advances, you can do cuts and all kinds of stuff. So this is yeah, one of the very basics that you need to understand also for going through this video. So anti-lag basically started out, as far as I know at least, with just retarding ignition timing and opening the throttle to compensate for the drop in engine power so that you still can idle the engine. And yeah, then probably people started introducing ignition cuts, and yeah, then you can get some kind of spool in this. Some further development from that then came from bypass valve use, so where you're bypassing air from the intake section and bypassing the engine and putting that air directly into the exhaust manifold. And then you can, yeah, increase the mass flow going into the turbine section without increasing the mass flow going through the engine. Of course, you can also increase the mass flow through the engine, and with the maintaining a correct air-fuel ratio in the exhaust manifold with the additional air from the bypass system, you can get and you have enough a high enough exhaust gas temperature in the manifold to ignite that mixture, or reignite the mixture, should I say. Then you can yeah, increase the mass flow and pressure ratio of the turbine in that way also. And then yeah, the most modern anti-lag function then takes this sort of quantized engine behavior into account. So you're running uneven cylinder setups basically. So you're running cylinder cuts with ignition retard, and this allows you to operate at a much wider range on the turbocharger. And that's mostly what we're going to be looking at today, because that allows for a higher maximum performance, and you're not as limited with both performance and reliability as with these sort of legacy anti-lag type systems. So to operate these modern type anti-lag systems, we need what we need to research and figure out about our engine package is what kind of operating sort of areas we can run this at. And this is basically to avoid misfires, and or yeah, as some people call them, ignition cuts. So that's basically just a deliberate misfire. And yeah, misfires are extremely dangerous. Most of the time you probably will get away with it without permanently damaging the engine, but it's a statistical thing. So sometimes you won't get away with it, and you will end up yeah, getting valves hitting the pistons and bending the valve stems, or even damaging the pistons. And of course this will, yeah, then your valves won't seat on the valve seats anymore. You can bump valves into other valves. And of course you will have big pressure fluctuations in the exhaust manifold and even the intake manifold, and this will create very uneven. Both the ECU will have incredibly difficult time managing the correct air-fuel ratio that you want on each specific cylinder for each stroke. And you will also have a very uneven performing engine, so we'll have this all kind of bucking and uneven running and this sort of semi-vibration type stuff in your drivetrain. And if you're running misfires or getting misfires or deliberate misfires at high load, so when you have very high boost pressure, you can even end up damaging your turbocharger. You can snap the shaft completely off the turbocharger. Depending on different turbocharger will be have different susceptibility levels to this type of a damage, but this is something that definitely can occur also. So something to keep in mind, and why to avoid misfires or ignition cuts at all possible costs. Okay, so we understand the basics of how this engine works and what we're talking about and what we want to achieve, maybe. So let's start getting our yeah, engine set up and stuff like this. So first of all, we want to look at the ignition system, because this is typically not very important for maximum power, as long as you have enough spark energy to ignite the mixture and produce power. But for running anti-lag systems, you really want to have very, very high both maximum spark voltage, so that you can run a large spark gap on your plugs, and also a high power, so that you get as long a spark duration as possible when your cylinder pressure goes down. This will allow you a sort of larger window to run your ignition timing at. So not more timing, but so you can run sort of worse timing, and you might gain some few degrees of ignition advance that you can retard the ignition further. And yeah, this will allow you to run a wider sort of operating range. And this is basically what we want to start looking at. But yeah, first we need, of course, to make sure that the engine is fully tuned. So you have the air fuel, the VE table tuned completely, and you understand where your minimum and maximum boost RPM are at, and what your knock limit is at the RPM range and stuff like this. So this sort of operating box where you want to operate the engine inside. So you also need to have your acceleration enrichment fully tuned, and by this probably also need to figure out your injection timing correctly, and you need to have your boost control set up to function correctly depending on your use case. So typically this will be a boost pressure target that you want to maintain, and you need to have your lookup tables correct for PID functions for that if you're using a traditional type setup. Or if you're running in a racing category with a restrictor plate on the intake manifold, like for instance our Rex engine is, or one option on our Rex engine is designed to run a 45mm FIA rallycross intake restrictor, then you really need to run a turbocharger or RPM target, because yeah, we can get into the details of that in some other video, but that is what you will want to be using in that case. Or potentially some kind of a hybrid system where you want to maintain a turbocharger RPM, but sort of part throttle stuff, you maybe want to do a boost pressure target or something like this. So let's get into the sort of more fun and dangerous stuff then. So you need to figure out what kind of ignition advance you can run on the engine. So while you have the full VE table running and everything is set up and ready to go without any kind of cuts or anything like that, you try to periodically retard your ignition timing. So depending on what kind of ECU you're using, you're going to have to figure out how to do this. On our XM system, we basically just have a system to cut one single cylinder, and then we look at the data log from that in kind of real time, and see if that sort of ignition retard on that one cylinder starts producing a misfire or not. And you probably might be able to hear this from the exhaust node also, depending on what kind of exhaust setup you have, or you might want to look at the exhaust manifold pressure sensor and see that you're not running into sort of pressure spikes or something like this, or if you have a really bad cases of misfire, you can end up having pressure spikes on your intake system also. So yeah, these are signs of misfire, and you want to look inside both your RPM range and your load range at how retarded ignition timing you can run without reaching misfires. And this is of course a statistical thing also, so you need to sample over multiple times to get sort of reasonably sure that you're not going to be running into misfires. And this operating range could be like up to even 5 degrees or something like this, where you sometimes have misfires and then you have less frequent misfires until you reach some kind of ignition advance where you almost never have misfires or never have misfires. And that's basically where you want to draw the line at. Okay, yeah, now I know how retarded timing I can run for different operating areas. And yeah, once you've done that, I mean, you need to, of course, write this down so that you know how to implement this when we start actually doing the tuning stuff. And the other thing you will need to look into then is the cylinder cut, and specifically when you're coming back from a cylinder cut, how much enrichment you're going to need to prevent a misfire when you're coming back after a cut. So on our XM system, for instance, we do this again by specifically cutting fueling from one cylinder on one stroke, and then checking the data log for the following stroke, like how much enrichment does that cylinder need to then create to have a combustible mixture in the cylinder. And then we pretty much know the sort of lean fire limit. Then it's easier, of course, to figure out from there, like how much do you need to enrich further from there to about have the same kind of air-fuel ratio as your other cylinders are, because you don't want to be on the lean limit, because that is a very NOx-sensitive area, of course, or depending on the engine, of course, but for most engines this will be true. And you also kind of want to look at, so you might end up with a problem also if your injection timing is really bad. So this is something you want to do in conjunction with injection timing, and want to move your injection timing around to need the least possible enrichment, because then your injection timing is correct. And this is basically both to reduce the amount of fuel that you're putting through the cylinder during the cut, and also so that And of course, so the extra enrichment needed for the following cycle is of course due to the amount of fuel, that is fuel film both on the intake ducting and the back of the intake valve. And if you're running a direct injection system, there is also some kind of a film sort of build up on the cylinder walls, or probably like above the compression ring, probably around the piston or something like that. I'm not really sure exactly where this sort of fuel buildup is. But yeah, that is what you need to do. And again, look at the RPM range and the sort of power range and figure out where your limits are on this. And when you're done with that, we're ready to go over to the next section. But before we go over to actually tuning the stuff, we need to think a little bit about what we want to achieve with this. And here is a sort of trade-off between maximum performance and sort of ease to drive or something like this. And this will depend very heavily on what kind of a driver you have, or if you're tuning your own car, of course you can choose for yourself and you don't need to take anything else into consideration. But typically you will have a quite reasonably big trade-off. And by big, I mean it might be like everything from between 1/10 of a second per lap to like even 1 second plus per lap or something like this, entirely depending on what you're doing with your car or motorcycle or whatever. So yeah, typically this is, I mean, if you want a really easy system, then easy car to drive, then you tune it so that you don't really have maximum power on tap at any specific time, so that if you come out of a corner, you can run at a slightly higher gear, so when you floor the throttle, you don't have full power immediately, and the engine builds up power a little bit smoothly to sort of help out with traction. But then you're also limiting performance, because in some situations where you're asking for maximum power, it takes a little bit of time for the engine to produce that power, and then you're losing performance. So by far, it's probably almost always faster to have the engine capable of producing maximum power immediately, and then it's just up to the driver to feed that power in according to traction situations. And of course, for rallycross, for instance, traction control is banned completely, and in some other racing categories you might be allowed to run traction control, so in that case there's probably no trade-off at all. You can just run maximum power setting basically all the time. So yeah, something to take into consideration. So when you start tuning your anti-lag settings, a very easy place to start is from a 0 power level. So basically, you're in neutral, keep the engine RPM constant at different RPMs. So you of course need to move inside of your operating window first. So there's no point in tuning boost pressure on anti-lag outside of your engine operating range, because as soon as you go off the anti-lag, then your turbo is going to spool down, or you're going to be in the surge area or something, so you don't want to be there, and you again don't want to be like outside of the more boost than what you want to run, or beyond the sort of choke area or anything like that. So yeah, you have your operating window, and this is where we're going to be tuning our anti-lag. So you start at basically 0 engine power, and you start retarding your ignition timing just like a flat retard, to start building up EGT. And while you're doing this, you're of course sapping engine power at the same time, so you need to increase throttle opening through your drive-by-wire throttle. You can get away with doing cable stuff and having some fixed opening, or even having some kind of like idle control valve type setup to like boost the cable opening or something, but that's just a complete nightmare, and yeah, we're not going to go through that. If you're running a cable type system, you'll just have to innovate and figure out how to make that work. I mean, it can be done, but it's lots of work that we don't want to get into here. When you're retarding ignition time, you will start to get into sort of EGT limits relatively soon, probably way before you reach your sort of maximum target boost levels. And so this will typically be around 900 to maybe 1500 degrees. So this is a Celsius, not Kelvin, for in case you're wondering which units we use here. And yeah, when you start reaching, so if you're in an area where you reach your EGT limits before you reach your turbocharger RPM target or boost pressure target, then yeah, what you need to do is start adding cylinder cuts in there. So this will drastically drop your EGTs, and this will help your turbocharger live longer, and also will help your exhaust valves. So depending on what type of engine you have, you will have different kind of maximum temperatures you can run on your exhaust valves before you start damaging either the valves or the valve seats, or yeah, potentially you can even have the valves stick on the guides, and then you will have a really bad day, because then it will start hitting the pistons and potentially the intake valves, and you will have big problems with that. So you start introducing cylinder cuts, and since you already checked the operating ranges of those, what kind of enrichments you will need and stuff like that, so you just implement those. And you start adding more cuts, and as you add more cuts, that reduces engine power more than retarding ignition timing, so you can open the throttle further. And this will of course increase your mass flow through the engine and allow you to run higher boost pressures, which increases mass flow again. And this will bring your temperatures down on the exhaust valves and the turbine section on the turbocharger also. And by doing this, you will be able to then run the sort of maximum retard that you can run without reaching misfires, that you again research already, so you know how much you can implement in different areas in your map. And since you won't statically be running there, because hopefully you have an ECU that is capable of running cuts smartly, so you don't end up cutting the same cylinders and just having some cylinders with really retarded ignition timing burning their exhaust valves, and some cylinders just running like with completely cool cylinders. So if you have an ECU that does that, bad luck. On our XM system we have coding to enforce that happens evenly, so we're not relying on randomness even, so we're actually enforcing that on our XM ECUs. And with this type of a setup, you typically will be able to max out your turbocharger RPM or boost pressure or whatever target. And then you just go through the RPM range and do that. However, you might be at lower RPM depending on how large of a turbine section and turbo you're running, and of course if you're running restrictors, then that reduces the efficiency of the package, so that again might require more energy to reach the sort of your desired results. So then it might actually be beneficial to use bypass valves, but of course using bypass valves you need to remember that you need to have a higher pressure on the intake side than at the exhaust side, because otherwise your gas flow is going to go in the wrong direction, and again you're going to have a bad day. So you need to take that into consideration, and that might limit you from running sort of maximum turbo RPM or reaching like the maximum boost levels, because especially like on restrictor engines, that typically will be very close to where you start having more back pressure, so more higher exhaust manifold pressure than intake manifold pressure, or like intake ducting pressure, and then you can't run bypass valve anymore, and then you can't have like immediate power when the driver floors the throttle pedal. So something to take into consideration with the bypass valve. And also, so you need to have of course a high enough exhaust gas temperature also, so your exhaust headers need to be glowing high enough, and you need to have a correct air fuel ratio in that manifold for there to be able to be combustion in there also. But in some situations it might be helpful. Okay, so now when we have the zero power area tuned, we want to start tuning the sort of the area between full power. Well, at full power of course you already have that tuned, so that's very easy. You want to produce the maximum amount of power out of the engine, so you're running typically, if you're not limited, maximum amount of ignition events you can run and maximum boost levels, and that's easy. But then you need to sort of blend in the areas in between. This will typically be easiest to do on a dyno, so you run at different part sort of pedal settings and then adjust the throttle settings and what kind of cylinder cut amounts and ignition retard and potential bypass valve blending you will need. So this will be highly dependent on what type of engine you're running, and you'll just need to play around with those a little bit and make that work. And this is of course reasonably static running sort of on a dyno. You can of course test like part throttle response and see what happens, but ultimately, because most ECUs will not have any kind of dynamic engine operation compensation like we do on our XM system, so you will need to do track testing and sort of get some kind of feedback on that, yeah, you will need to compensate your sort of static lookup tables so that the dynamic situations work sort of more logically. But yeah, typically you will get sort of reasonably close to theoretical maximum performance, so you might not be giving up too much performance there. So now that we have this sort of maximum performance capable anti-lag tune-up done, so this is again, yeah, this way you will tune for performance, and then yeah, if you want to have sort of a easier to drive setup, then you of course, yeah, just tune so that your setup is below those limits. And it's kind of a similar trade-off also with the launch control setup. So with launch control, you want, I mean, for drag racing guys out there, you know that yeah, the sort of initial sort of acceleration you can reach and how the tire behaves is incredibly critical for performance. So we can see how you sort of, yeah, get a trade-off on that. So you can do a reasonably sort of safer tune that allows sort of more consistent launches, but then you're also giving up performance potential. And let's look at yeah, how this is typically done on a rallycross car. So you can see from that the basic launch system is you're doing so I mean I don't have access to this information, but I mean, yeah, it's reasonably clear how this works. So you're using a sort of inertia bomb basically to get the tires moving while you're keeping the engine from producing any power at all, and this basically limits the tires from spinning out of control and you just getting stuck on not moving forward at all with the tires just spinning wildly. So you're dumping the clutch at very high RPM, and you tune this RPM to get the sort of inertia correct. And then when the engine RPM drops low enough, then you basically start ramping in engine power, and you probably have some either RPM dependent or time sort of scaled RPM dependent sort of engine power increase that you tune for different kind of traction situations. Then if your traction situation isn't exactly as you tuned for, you won't get into the situation where you're just wildly spinning your tires and everyone else is just pulling way away. So, but also you're giving up the potential for maximum performance, and we're all about maximum performance, so let's go through that type of a setup here. So what we want to do with this is to maximize the performance right when we're moving off. So this means that we're not spinning the tires this sort of first 30 centimeters or 1 meter or even 3-4 meters or something like this. And to do this, of course, we have to slip the clutch, and this also produces some problems, but also gains us some benefits. So in this case, we typically would tune the launch control system to run a relatively low RPM. So instead of revving the engine at like 8,000 or 9,000 RPM and using the inertia from that to pull the car forward, we'll typically build up maximum boost pressure at say 4,500 RPM or something like this, and then have a either, I mean, if you have a smart system and can run a PID type thing for launch control, then you can maintain RPM, but it's critical that the engine has to run smoothly and allow a different sort of engine load while maintaining smooth running, because the driver needs to be able to load up the drivetrain with the clutch while keeping the car stationary with the brakes. And this helps actually twofold. So it helps preload the suspension system a little bit, so you won't get this like movement that lifts up the front tires and ends up losing overall traction. And you will also, when you launch, sort of have a sort of shorter reaction time there while maintaining a sort of maximum traction level. And I mean, you can of course put in restrictors in your hydraulic line to the clutch and stuff like this, and tune that to get some kind of a clutch release speed with some pressure limiters or something like this, of course, also potentially. I mean, very, very easy stuff to do. And with this type of a setup, so you build a boost pressure on the launch control system, And then the driver will start releasing the clutch and loading up the drivetrain, of course, while holding the handbrake to really keep the car in place. And then at the correct or time, so when the start lights turn green, or if you're doing drag racing, when the tree timing is correct, you release the brake, release the launch control button to allow the engine RPM to increase, and then you release the clutch. So either slip the clutch further out, or if you have some tuned restrictor system or something like that, then just sidestep the clutch and let the clutch release at the set time you have that tuned for. And this will allow you to launch without having any kind of wheel spin at all. And this will, of course, give you higher potential for performance there. And this can be very significant for, especially for drag racing use, but also for rallycross stuff, where the launch off the line and who is first into the first corner is really important, because the tracks are so slow that overtaking is relatively difficult. So it's important to be first into the first turn. So what does all of this have to do with us here at Elmer Racing then? Well, our custom race engines, so both our Thor engine and our Rex engine, are designed to be able to run anti-lag stuff. On our Thor engine, that's typically not needed, but of course, for drag racing use, you of course want to run anti-lag launch control. They're pretty much the same thing for performance and reliability type launch control stuff. If you have these two-step things, or like misfires, ignition cuts, whatever you want to call them, then that is not something that we want to see here. So performance-oriented anti-lag launch control stuff. So we have those designed to run basically two port injectors per cylinder, because it's a 4-valve head, so you have two intake valves, and we want to reduce the amount of wall wetting possible as much as possible on the ports. So we have the injectors and the spray pattern on those are selected together to keep the wall wetting as low as possible. And then we also dimension the injector size recommendations, or typically if we provide a complete engine, then the injector size that is on that engine to be able to run sort of fully sequential injection, or whatever this would be called, so that we're injecting fuel only while the intake valve is open. Or this needs to be timed, of course, because the fuel droplets have some velocity when they come out of the injector, and they're not immediately at the valve face. So this is why you need to tune the timing that we went through previously. And this is something that we go through, of course, on our Rex engine, where very heavy anti-lag use and launch control is expected and sort of normal running. Of course, it will reduce longevity on the engine, but it needs to somehow cope with this. So we run cooled Inconel exhaust valves in this case on that, and very high quality exhaust valve seats to keep sort of higher maximum operating temperatures for those components. Otherwise our Rex engine is sort of a budget option, so it's not as high tech as our Thor engine. But this is the single aspect there that is really state of the art on our Rex engine. And we also, so the fuel injectors are of course really close to the valves in this case. That will give kind of poor fuel mixing, so to compensate for this, we also recommend running high quality injectors with really good quality spray patterns, and also recommend running a maximum possible fuel pressure that the injectors will reliably operate at. So this will produce smaller fuel droplets and will vaporize the fuel quicker then, and give a better mixture. And of course tuning the injection timing correctly also will help with that. And so far it has been okay up to 9,500 RPM that we've tested so far. So it seems good. So no need to have injectors like right at the end of the intake duct or something like this, because that will produce big problems when you want to start cutting cylinders. But we do take this heavily into consideration on our engines. So bonus news or fact, or whatever you would call that, for you guys that stuck to the end, or you smart guys that just jumped over the rest of the stuff and jumped directly here. So we have tested now on our Rex engine also. So we manufacture billet collectors, of course, which you might or might not know. But we're the sole manufacturer in the world for those currently. And so we have a collector set up with the twin scroll turbocharger. So basically run the exhaust gases through one scroll on the turbocharger normally. Then we have a wastegate that will, sort of once we reach target boost pressure, we open a wastegate and allow flow through the second scroll on the turbocharger also. And this slightly increases the efficiency that you get from the turbocharger, sort of widens the operating range slightly, or however you want to see that situation. And this is actually, really good now that we have information on this, and especially for like tight racing categories where you want to absolutely maximize your efficiency you can get out of your entire package. This will gain you some like 1%, maybe 2%, something like this, but those might be 2% that are not available from anywhere else. So definitely something that you want to look into. Or on the street, you could potentially get boost at a lower RPM or get a quicker throttle response, or a boost response, should I say, something like this. So definitely a worthwhile technology. And we currently have this set up so we can run with off-the-shelf 38mm turbo smart wastegate. But this is limited to relatively small turbine housings and small turbos, because our wastegate doesn't simply flow enough to be able to allow this on really big turbos. But we are working on this, and we will be coming out, what would I guess, probably within a few months or something like this, with more information on this similar type of wastegate setup for the second scroll for larger turbochargers also. So potentially smaller, although I think the 38mm probably will be okay for smaller setups also without big problems. So yeah, something to look forward to. But yeah, this was a recap on our Rex engine, some updates on our wastegate, integrated wastegate collector setup with the using the 2 scrolls on a twin scroll turbocharger, and anti-lag for dummies. So hope you guys are much smarter about that. And hope you guys had fun. I'm Oscar from Elmer Racing. See you in the next one.